Hello. In this video I'd like to pick up where we left off from yesterday. We're starting our lesson number 2 in part 1 of unit 4 for college algebra, and in this video we're going to cover composition of functions again along with function inverses. Now in the last video I did have a block of practice problems that I said would be good for practice. One thing that I wanted to start off with this video in doing is showing you a sample solution to a problem like number 11. I know that there is a lot of work that goes into this entire block. I do feel that if you practice all of these, you'll be very, very comfortable with anything that you see in our upcoming test. But even if you don't complete them all, I think sharing this method of attack would be a good approach for you. So in problem number 11, we were told that f of x is equal to 2x and that g of x was equal to 3x squared, and then we need, or 3x squared plus 1. And then we needed to evaluate f of g at 4, g of f at 2, f of f at 1, and g of g at 0. We had to do all 4 of these parts for every single problem. Now the way I would personally approach each of these is I would do it in 2 parts. I would compose the functions with x first, simplify that, and then use that simplified result to answer the question at hand. So in 11 part A, we should compose f with g. So f is our outer function, g is our inner function. And so I use the outer function 2 times something. The something happens to be the inner function g, so 3x plus 1. When simplified, or distributed in this case, we're left with 6x squared plus 2. Well, now that I know that f composed with g at x is 6x squared plus 2, then when I need to evaluate f composed with g at 4, I can simply change the letter x to the number 4 and evaluate the result. Similarly, for part B, g composed with f at x would be 3 times something squared plus 1. The something that's being squared in this case is the function f, so I placed 2x inside of that position since f was defined as 2x. When simplified using the order of operations, we square the 2x first, and that gave me 4x squared. Then I can multiply that result by 3 and then add 1 at the end. Unlike terms can't be combined, so I leave this expression as 12x squared plus 1. Now that I have the function g composed with f at x, I can compose g with f at 2 by simply changing the letter x to the number 2 and evaluate the result. So that's an approach or a technique that I would use for each of these problems that you do work on. If you end up not doing all of them but want just a few to focus on, then I think these would be good numbers to practice against. If you'd like clarification on your work for these numbers, just let me know and I'll respond. You can send those to me through email or through Schoology, and I'll respond back with some additional information on how you've done on them. Or you can bring those to class and we can talk about them there too. In the last video, we got to the point where we were verifying or determining the domain of a composite function. So I wanted to cover that in this video first, or well, second. And then to round out the video, to wrap it up, we will talk about function inverses. Okay, so we're going to use the instructions that I gave you in the first set of videos, the process I should say listed here, A through D. So the first thing that we need to do is identify the restriction of the inner function. Then we need to identify the restriction of the outer function. We're going to write a simple equation that sets the inner function not equal to the restriction of the outer, because we don't want the result of our inner function to become a restriction of the outer function. And then we'll combine 1 and 3. So I should be labeling these 1, 2, 3, and 4. And so we'll combine our answers from part 1 and part 3. So let's go after it here. In number 21, we are combining f with g, so that means that g is our inner function. We know that because it's on the right side of our composition notation, and f is our outer. So in part A, or step number 1, identify the restriction of the inner function. Well, if I've got g of x that equals 2 over x, the only restrictions that I see here, because of this being a fraction, is that x is not allowed to equal 0. I can substitute any number into this fraction except for the number 0 and still get a real number result back. So our restriction for part 1 is that x is not allowed to be 0. For part 2, we identify the restriction of the outer function. Now the outer function happens to be 3 divided by x minus 1. And this restriction, I think, can be found pretty easily too. We don't want the denominator to equal 0, so we don't want x minus 1 to equal 0. So therefore, x is not allowed to equal the number 1. We treat these not equal to signs just like an equals sign when solving, so I added 1 to both sides, and I found that x is not allowed to equal 1. As long as we substitute any number into this equation other than the number 1, then we will obtain a real number result back. Step 3, we set the inner function, 2 over x in this case, not equal to the restriction of the outer function. We can't let the result of this inner function, 2 over x, ever be equal to the restriction of the outer function. So 2 divided by what number equals 1? Well, we can multiply both sides by x if you wanted to. And now you've got 2 equals 1x, or in other words, 2 is not equal to x. So let's think about that for a second. Well, if 2 divided by 2 was evaluated, if x was ever equal to 2, we'd have 2 divided by 2, which equals 1, and that result gets placed inside of this function, 1. Well, we just said a second ago that 1 is not allowed to be used in this function. So if x was ever equal to 2 on the inside, it ends up producing a 1 as a result for that inner function, and therefore that's used as the input of the outer function, which again is no good. So as far as our restrictions go in the grand scheme of things, we are not allowed to use 0 because of the inner function restriction, and we cannot use the number 2 because of the outer function restriction. In the composite function, it is okay to use the number 1. This one will be okay in the composite. It's okay to use in the composite because when we plug it into the inner function, it will be changed to a number other than 1 by the time we introduce it in the outer function. So for our final answer, when we're trying to restrict or identify the domain of the composition of functions, we're going to say something like this, that x is not permitted, not equal to the number 0 or 2. Now, it would be helpful to know what that composite function would look like, so let's just double check that real quick. If I did compose, and I'll use a different colored ink here for a second, if I did compose f with g in that order, what we would end up with is 3 divided by something minus 1. So my outer function is 3 divided by something minus 1. The something happens to be 2 over x. And we could probably use some algebra to simplify this, but I don't think it's really necessary here. What we're saying is that in this composed function, 3 divided by 2 over x minus 1, in that composite function, the x values that can be used are nearly infinite. Well, I guess we could say that there's an infinite number of x values that can be used except for the x values 0 and 2. If we were to ever substitute the number 0 or 2 into this expression or this equation, we would end up with a non-real result. So let's try that with number 22 as well. Got those instructions moved out of the way so that we can do this. All right, step number 1, identify the restriction of the inner function. Well, we're again composing f with g, so we've got the inner function at g and the outer function at f. If the order had been switched, we would switch the order in these steps, but we're using the same composite in the same order as we did before. So as far as our inner function goes, we don't want negative 2 over x to be undefined. So what numbers would make this undefined? Well, as we've seen before, the fraction in this case can't have a denominator equal to 0, so we don't want to let x be 0. So we're going to say our restriction is that x is not allowed to be 0. For number 2, the restriction of our outer function. Now our outer function is 1 over x plus 3. So this is pretty easy. We are not allowed to have x plus 3 to equal 0, and therefore as long as x itself is not equal to negative 3, then we're going to be in pretty good shape. As long as the result from the inner function doesn't equal a restriction on the outer function, then we'd be good to go, but there are times where that might happen. So for step 3, we will set the inner function, negative 2 over x in this case, equal to our restriction of the outer function, negative 3, and we'll decide or determine what numbers makes that happen, or true. Well, again, I can multiply both sides by x, and we're left with negative 2 cannot equal negative 3 times x. We would then divide both sides by negative 3 and find that 2/3 is not permitted for our value x. So for our final answer, step number 4, we're going to combine the restrictions from step number 1, which was the number 0, and the restrictions from step number 3, which was 2/3, and we would say that the domain restriction for this composite function in that order would be 0 and 2/3. I've got one more example because I know they show up in Math Excel involving radicals, so I thought I'd just walk through this one as well. We're again going to pretend that f is composed with g in that order, so we'd like to find the restriction of the composite function f with g. So g is acting as our inner function and f is acting as our outer function. For step number 1, what are the restrictions for the inner function? What numbers could I plug into or substitute in for x that produce a non-real result? Well, as it turns out, there are none. Right? There are no restrictions with this particular function. Any real number that's substituted into this expression will calculate out to be a real number as a result. So for step 1, we have no restrictions. For step 2, what we don't want to see are non-real results for this square root. Now, in the examples of before, we just considered a denominator and when that would be equal to 0, but that's not necessarily the case with a square root. What we want to avoid here are negative numbers inside of the square root. We certainly can find the square root of 0, and we can certainly find the square root of any decimal, but what we can't find in the real number system is the square root of a negative number. So anything like negative 1 or negative 2 or negative 3 or so on would be a restriction. So if I'm noting here, and maybe I should have done that in this first line too, that with g of x being 2x plus 3, there were no restrictions, but with f of x being the square root of x, what we're worried about here, what the restrictions are that x must remain greater than or equal to 0. So as far as our restrictions go, let's say that x must be greater than or equal to 0. I won't use that inequality symbol anymore, or I'm sorry, the not equal sign in this case, because what I'm doing is I'm specifying what x values should be. X must be greater than or equal to 0. So then for part 3, if I set the g of x function, in this case 2x plus 3, to the domain restriction of part 2, I'm going to specify that 2x plus 3 must be greater than or equal to 0. Now here again, f composed with g, and I'm terrible about doing this because I didn't show this before, but I'll point it out now. F composed with g would look like this, the square root of something which happens to be 2x plus 3. If I were to ever use this function, the square root of 2x plus 3, I would have to recognize which values are not permitted for use in that function. And we're in the middle of that right now. If 2x plus 3 must be greater than or equal to 0 in accordance with the combination of step 1 and step 2, then we could subtract x from both sides across from this inequality, and that's fine. And then divide by 2, and we would see that x must be greater than negative 3 divided by 2, or negative 3 halves. So then when we combine our answers for step 4, the restrictions for the composite function would be the combination of 1 and 3. So if there are no restrictions from step 1, so no restrictions combined with these restrictions here in step 3, then we would simply say that for the composite function, in all cases, x must be greater than or equal to negative 3/2. And as I said before, I'd like to finish out this video by talking about inverses, because when we talk about function inverses, we inevitably do so in the context of composite functions. A function and its inverse composed with one another will always equal the variable x, or whatever your independent variable is. And we use inverses to undo or solve larger equations. We've talked about this in the past, specifically in Unit 2. So I've got an example from that practice set 4 of f of x equals the square root of x plus 1. I would like for us to find the inverse and then verify that we've found the inverse. So the instructions might look something like this, perhaps worded a little bit differently, but essentially we're going to be finding the inverse, and this notation is what we use to identify the inverse, and then we need to verify that we found the inverses by performing a check. Well, if you recall, finding the inverse starts by first rewriting the equation. Instead of using f of x notation, we are going to use the letter y. We have the square root of x plus 1. Then, to find the inverse, or to continue finding the inverse, since it's essentially the opposite of the original problem, we're going to switch the letters x and y. So we've essentially switched or found the reverse of the letters, and now we're going to isolate or solve for this y value. That shouldn't be too hard to do. If I square both sides of the equation, I'm left with x squared equals y plus 1. And if I subtract 1 from both sides of the equation, I'm left with y equals x squared minus 1. Now this y that we ended with is not the same as the y value we started with. The original y value happened to represent f of x. This new y value represents f inverse of x, or the inverse of our original function f. And so our claim here is that x squared minus 1 is the perfect and complete opposite, or inverse, of the original. Right? We're going to make the claim that these two are inverses. And now step 1 is done. We found the inverse. But how do we verify? Well, if you recall from the lessons in the past, to verify, we need to compose f with f inverse at x, and we need to do this both directions. We need to compose f inverse with f at x. We have to check both of them, because we could find an inverse in one direction but not the other, and then we wouldn't have found an inverse after all. So composing f with f inverse, the outer function is f and the inner function is f inverse. Let's set that up. The outer function, f, is the square root of something plus 1. The something happens to be x squared minus 1, so we'll make that substitution. We're placing this function inside of the original. If we follow the order of operations, we must simplify anything inside the parentheses first, which can't be done. Then we'll follow the order inside the larger grouping symbol. In this case, the radical sign is acting as a grouping symbol. So I have x squared minus 1 plus 1. The minus 1 and plus 1 can be combined, and we're left with x squared. And then lastly, the square root of x squared is indeed x. That's a good sign for us, because when f is composed with f inverse in this order, we end up with x, which is our ultimate goal. That's how we described inverses in the past. We also need to check in the other direction. So if we use f inverse as our outer function, that would be something squared minus 1. Something squared minus 1. That's our outer function. The inner function happens to be the square root of x plus 1. And when simplifying this expression, well, we have the square root of a group that's being squared. And within the order of operations, we should apply this square to the square root, not to the inside underneath it. That's an inner parentheses that can't be affected just yet by that exponential. So when we square a square root, that leaves us with x plus 1, or the inner of that, or the argument of that square root. And x plus 1, take away 1, of course, is x, which is a good sign for us as well. We've now seen that the composition in both directions ends up equaling x, so we have now verified that this indeed was the inverse. So finding it requires just a little bit of math by reversing the x and y and solving for the new y value. Verifying requires a pair of composite functions. That was a lot to cover in this relatively short video compared to some of the video lengths that I've produced in the past. Hopefully this gives you something to think about and gives you something to work on, and it assists you with your Math Excel work for this week. If you have further questions, please let me know. Otherwise, thanks for watching.